Okay, so you've spent all this time learning how to tell if an infinite series converges, and that's a huge step, but it leads to a much more practical question. So it converges, cool, but what does it converge to? And maybe even more importantly, if we can only get an estimate, how do we know if our guess is any good? Today, we're shifting gears from theory to practice.
And this isn't just some abstract math problem. It's a central challenge for scientists and engineers everywhere. The truth is, for most series out there, finding the exact sum is, well, it's impossible. So our job kind of turns into being a detective. How close can we get to the real answer, and how can we be sure about the margin of error?
So here's our game plan for today. First, we'll talk about why finding that perfect sum is often a lost cause. Then, we'll clearly define what we mean by error. After that, we'll get into the good stuff, our two main tools for hunting down that error: the integral bound and the alternating bound. And of course, we'll wrap up by seeing them in action with a couple of examples.
You know, unless you get lucky with a really nice geometric series or something, you run into a fundamental problem. You just can't add up an infinite number of things. I mean, you'd be adding forever. It's a process that would literally never end, which means we've got to get clever.
And this is a really key idea to grasp. Approximation isn't us being lazy or taking a shortcut. For the vast majority of series, it's a mathematical necessity. It's literally the only tool we have to give these things a practical, useful value. And that's why knowing just how good our approximation is, well, that becomes everything.
So if we're going to talk about the quality of our guess, we need to know who our main suspects are. In this little detective story, you've got your best guess, and then you've got the error, which is like the piece of the puzzle that's still missing.
First up is our best guess. We call this the partial sum, or S sub n. This is the piece we can actually get our hands on. We just decide, hey, let's add up the first 10 terms, or 100, or 1,000, and whatever that sum is, that's our working estimate.
And that leads us to the other player, the remainder, R sub n. This is the error. It's everything else, that whole infinite tail of the series that we just ignored. It's the precise difference between the true hidden sum S and our calculated guess S sub n. Our whole mission today is to figure out just how big this remainder is. Now here's the really clever part. Think about it. Finding the exact error would mean we know the exact sum, and we've already said that's pretty much impossible. So instead we just need to trap it, put a ceiling on it. Our goal is to find the number where we can say with total confidence, I don't know exactly what the error is, but I know for sure it's not bigger than this. Okay, let's grab our first tool from the toolbox. This is the integral bound, and it's a super powerful way to connect the choppy, step-by-step world of a series with the smooth, continuous world of an integral. But, and this is a big but, you can't just use it anywhere. It has some rules. Yeah, there's a 3-point checklist you have to go through first. The function that matches your series has to be continuous, positive, and decreasing. All three, no exceptions. Why? Because if those things are true, we can guarantee that the sum of our series behaves nicely with the area under the curve. If we get 3 green check marks, we're good to go. And this is what it all boils down to, this big inequality right here. What it's saying is that our error, that R sub n, is literally trapped, sandwiched between the values of two integrals. And for our purposes, we really care about that right-hand side. It tells us that the error is at most the value of the integral from n to infinity. We calculate that integral, and boom, we found our maximum possible error. Okay, but what happens when things aren't always positive? What if the signs keep flipping back and forth, plus, minus, plus, minus? Well, for that, we have our second tool. And honestly, this one is so simple it almost feels like cheating. It's the alternating series bound. With this tool, you can forget about checking 3 conditions. Forget about doing any complicated integrals. If you've got a convergent alternating series, finding the error bound is just way easier. In fact, here's the whole idea right here. The size of your error is always smaller than the very next term you didn't add. That's it. Seriously. Your error is guaranteed to be less than the absolute value of that next term b sub n plus 1.
Just think about that for a second. You make your guess, sum, right? The true sum, the real answer, is hiding right next to it. And how far away can it be? No farther than the size of that first term you ignored. It's just a beautiful, simple, and super powerful concept. All right, enough talk. We've got our 2 shiny new tools. Let's actually put them to work. We're going to tackle a couple of problems and see how these methods crack the case. Okay, case number 1. Take a look at this series. The second you see that -1 to a power thing, alarm bells should be going off in your head screaming alternating, alternating.
And the question is, how many terms do we have to add up to be sure our error is smaller than 0.001?
This is a job for our alternating series tool. The rule is simple. The next term, b sub n plus 1, has to be smaller than our target error of 0.001. So we set up the inequality 1 over n plus 1 to the fourth has to be less than 1 over 1,000. Flip that around, and we get that n plus 1 to the fourth has to be bigger than 1,000. From here, it's just guess and check. Let's try 5. 5 to the fourth, that's 625. Nope, too small. How about 6? 6 to the fourth is 1296. Bingo, that works. So if n plus 1 is 6, then n must be 5. That's our answer. We just need to add up the first 5 terms.
So we just do it. We plug in n equals 1, 2, 3, 4, and 5. That's 1 minus 1/16 plus 1/81, and so on. Punch that into a calculator and you get about 0.9475. And the best part? We know for a fact that this number is within our target range, less than 1,000th away from the real answer.
All right, on to case number 2. This time we're looking at the sum of 1 over n squared. Now hopefully you recognize this one. It's a classic convergent p-series. It passes our checklist, right? It's positive, it's continuous, and it's always decreasing. That makes it a perfect job for our integral bound tool. The mission is, if we calculate the sum of the first 10 terms, what's the absolute biggest our error could be?
Okay, let's just walk through the process. Our error, r sub 10, has to be less than or equal to the integral from 10 to infinity of 1 over x squared. First step, find the antiderivative. That's negative 1 over x. Now we evaluate it. The limit as x goes to infinity is just 0. Then we subtract what we get when we plug in 10. So that's 0 minus negative 1/10. And just like that, we have our answer, 0.1. The maximum possible error is 1/10. So what does that mean? It means if you add up the first 10 terms, your answer is guaranteed to be off from the true final sum by no more than 0.1. That's our bound.
All right, let's pull it all together. What are the big takeaways here? First, and most importantly, we almost never get the exact sum. We have to approximate. But that's no big deal because we have some awesome tools to measure our error. For those nice positive decreasing series, the integral test sets up a boundary for the error. And for alternating series, it's even simpler. The error is always smaller than the next term in line.
And that really leads to the biggest question of all, one that goes way beyond the classroom. I mean, think about it. Engineers designing a bridge, physicists calculating a satellite's orbit. They are using these approximations all the time. The math can tell you exactly how big your error might be, but it can't tell you how much error is acceptable. At what point is our estimate good enough to build that bridge or launch that rocket? And that's where the pure math ends and the real-world engineering and judgment begins.